G'day and welcome. Have you ever looked up at the night sky, at the countless stars scattered across the darkness, and wondered what it's all made of? We live in a universe filled with an incredible amount of stuff. We have planets, stars, vast galaxies, and enormous clusters of galaxies. All of this, everything we can see, touch, and measure, is made of what we call matter. You are made of matter. The device you're watching this on is made of matter. The earth beneath your feet is made of matter. But what if I told you that, according to our best understanding of the universe's beginnings, none of this should be here? This brings us to one of the most profound and baffling questions in all of science. According to the theories that describe the birth of our universe, the Big Bang should have created equal amounts of matter and its mysterious twin, antimatter. For every particle of matter, like a proton or an electron, an identical antiparticle should have popped into existence. Think of it as a perfect cosmic balance, a complete symmetry between the two. This isn't just a wild guess, it's a direct prediction from the fundamental laws of physics. So the early universe should have been a perfectly balanced sea of both matter and antimatter. But when we look around today, we see a very different picture. The universe is overwhelmingly dominated by matter. There's no sign of anti-galaxies, anti-stars, or anti-planets anywhere we look. It's as if one side of the cosmic equation has almost completely vanished. This glaring discrepancy is what physicists call the baryon asymmetry problem. It's a fancy name for a simple but massive puzzle. Where did all the antimatter go? Why does our universe show such a strong preference for matter, when the laws of physics insist it should have been created in perfect balance with its counterpart? The consequences of this imbalance are nothing short of our own existence. If the Big Bang had indeed produced a perfectly symmetrical universe, with one particle of matter for every one particle of antimatter, the story of the cosmos would have been very short and very boring. The matter and antimatter would have quickly found each other and annihilated in a flash of pure energy, leaving behind a universe filled with nothing but light. No atoms, no molecules, no stars, no planets, and certainly no us. The fact that we are here, able to ask this very question, is the ultimate proof that the perfect symmetry was broken. Something tipped the scales, and that something is the universe's biggest mystery. So what exactly is this antimatter I'm talking about? It might sound like something straight out of science fiction, an exotic substance used to power starships across the galaxy. While it is certainly fascinating, antimatter is very real. It was first predicted in 1928 by the brilliant physicist Paul Dirac, who was working on an equation to describe the behavior of electrons. He found that his maths worked perfectly, but it had a strange quirk. It predicted the existence of another particle, identical to the electron in every way, but with the opposite electrical charge. This anti-electron, later named the positron, was discovered just a few years later, confirming Dirac's incredible insight. This is the key to understanding antimatter. Every particle of matter has a corresponding antiparticle. They have the same mass but opposite properties, like electrical charge. When a particle meets its antiparticle, they don't just collide, they annihilate each other completely. Their mass is converted into a burst of pure energy, following Einstein's famous equation, E equals mc squared. This process is the most efficient energy release known to science, far more powerful than any chemical or nuclear reaction. It's a fundamental rule of the cosmic dance. Let's rewind the clock all the way back to the beginning. We're talking about the first fraction of a second after the Big Bang. At this moment, the universe was not the vast, cold, and dark place we know today. It was unimaginably hot and dense, a point of infinite density and temperature from which everything would emerge. This primordial state was a chaotic furnace of pure energy, more extreme than the core of the most massive star. It was within this cosmic crucible that the fundamental particles of matter and antimatter were forged. The energy levels were so high that energy could spontaneously transform into mass, following the principles laid out by Einstein's famous equation, E equals mc squared. This process is known as pair production. High-energy photons, particles of light, would spontaneously transform into pairs like an electron and a positron, or a quark and an antiquark. The early universe was a dynamic, seething soup where matter and antimatter were continuously popping in and out of existence, locked in a frantic dance of creation and destruction. It was a perfect equilibrium, a state of absolute chaos and balance. This creation wasn't limited to just one type of particle. The energy was so immense that all the fundamental particles we know from the Standard Model were being produced. The universe was a rich stew containing every possible ingredient. This period, lasting for less than a second, was the only time in cosmic history when matter and antimatter existed on an equal footing. Our best description of the subatomic world, the Standard Model of particle physics, is built on the principle of symmetry. It predicts that the laws of physics should apply equally to matter and antimatter. According to this picture, the Big Bang should have been the ultimate impartial creator, meticulously producing one antiparticle for every single particle. This expectation of perfect balance is not just an aesthetic preference. It is a core prediction of the physics that has been proven correct time and time again in our laboratories. Imagine the universe in that first microsecond. It's a roiling sea of particles. For every proton, there is an antiproton. For every electron, a positron. For every neutron, an antineutron. The idea was that as the universe expanded and cooled, these particles and antiparticles would simply annihilate each other, leaving behind a universe devoid of any matter. This would result in a cosmos filled only with photons, a sea of light, but no substance. This theoretical universe, born from perfect symmetry, would be a very different place from the one we inhabit. We are here, living on a planet made of matter, orbiting a star made of matter, in a galaxy made of matter. The existence of our complex, matter-filled universe is the most powerful evidence that this picture of perfect, unbroken symmetry cannot be the whole story. Something must have intervened to break the rules. The universe did not remain a hot, dense furnace forever. The initial explosion of the Big Bang sent space itself expanding outwards, a process that continues to this day. As the universe expanded, it began to cool down. This cooling had profound consequences for the matter-antimatter soup. As the overall energy level dropped, it eventually fell below the threshold required for pair production. While the creation of new pairs ceased, the second half of the cycle, annihilation, continued with ruthless efficiency. With no new particles being formed, the existing particles and antiparticles kept finding each other and converting back into energy. This was the Great Annihilation event. If the initial balance had been perfect, as our theories suggested, this process should have been complete. Every single particle should have found its antiparticle partner, and they should have all cancelled each other out, leaving behind a universe with no matter at all. The universe should be an empty, sterile place, a faint afterglow of a perfectly balanced but ultimately fruitless creation event. The fact that we can observe stars and galaxies is a direct refutation of this expected outcome. Our very existence is proof that the symmetry was not perfect. For the universe we see today to exist, there must have been a slight imbalance from the very beginning. For every billion antiparticles, there must have been 1,000,000,001 particles. Cosmologists have studied the leftover radiation from the Big Bang, known as the cosmic microwave background, with incredible precision. By measuring the number of photons in this background radiation and comparing it to the estimated number of baryons in the universe, scientists have been able to calculate the ratio of matter that survived. The result is both mind-boggling and profound. It all came down to a tiny, almost insignificant asymmetry. The data suggests that for every 1,000,000,000 antiparticles in the early universe, there were 1,000,000,001 particles of matter. It's an incredibly slight preference, a cosmic rounding error. When the Great Annihilation took place, the billion-particle-antiparticle pairs dutifully cancelled each other out, disappearing into a sea of photons as predicted. However, that one extra particle of matter in every billion was left over, with no antiparticle partner to destroy it. This lonely survivor, repeated across the cosmos, became the seed of everything that would follow. It's a staggering thought. Our entire existence is owed to this 1 in a billion leftover. Every star you see in the night sky, every galaxy spinning in the void, every planet, every rock, and every living thing is made from this cosmic remnant. The specific value of this asymmetry seems to be finely tuned to allow for a universe like ours to exist, one that is rich with structure and complexity, a place where life could eventually emerge. This raises the ultimate question: what caused this life-saving imbalance? Why was there one extra particle of matter for every billion antiparticles? This is not something the standard model of particle physics can explain. Think about that for a moment. Everything we know, everything we hold dear, is essentially cosmic scrap. We are living in a universe built from the leftovers of a much grander, more symmetrical state. The vast majority of the matter and antimatter created in the Big Bang fulfilled its destiny and annihilated, becoming the radiation that still permeates the cosmos today as the cosmic microwave background. What we think of as the stuff of the universe is actually just the tiny, almost negligible fraction that managed to survive this cataclysm. Our solid, tangible world is the exception, not the rule. We are the improbable survivors of a cosmic war that wiped out almost everything. This perspective completely changes how we view our place in the cosmos. We are not the primary product of the Big Bang, but rather a fortunate byproduct of a subtle imperfection in its creation. It's a humbling thought. This makes the existence of structures like galaxies, stars, and planets, and ultimately life, all the more precious and remarkable. We exist because of a flaw in the grand cosmic design, a small crack in the perfect symmetry of the laws of nature. This annihilation problem is therefore not just a problem, it's also our origin story. It's the reason we are here to ask the question in the first place. The answer is not just a footnote in a physics textbook. It would represent a revolution in our understanding of the fundamental laws of nature. It would tell us about the conditions at the very instant of creation and reveal the new physics that lies beyond our current theories. So, how can we be so sure that the universe is dominated by matter? It's a bold claim, considering the sheer scale of the cosmos. Perhaps there are vast regions of space filled with antimatter, separated from our matter-filled domain. To check this, astronomers have conducted a great cosmic survey, meticulously observing the universe on the largest scales. They look for the telltale signs that would give away the presence of antimatter galaxies. The primary method for this cosmic search is to look for the signature of annihilation. If a galaxy made of matter were to collide with a galaxy made of antimatter, the result would be spectacular. This would release an enormous flood of high-energy gamma rays with a very specific energy signature. Astronomers have spent decades scanning the skies for just such a signal, especially from the spaces between galaxy clusters where such a boundary might exist. After years of searching with powerful gamma-ray telescopes, the results are conclusive. We have found nothing. There are no vast clouds of annihilation radiation lighting up the voids between galaxies. This lack of evidence is incredibly powerful. It tells us that, at least on the scale of galaxy clusters, our observable universe is made entirely of one type of stuff, our kind of matter. The search for antimatter doesn't stop at the edges of galaxy clusters. Scientists have also looked for more subtle clues within our own Milky Way galaxy and its neighbors. If, for instance, a star made of antimatter existed within our galaxy, it would be constantly interacting with the interstellar medium, the thin gas and dust made of normal matter that fills the space between stars. While we haven't found any anti-stars or anti-galaxies, we do have one direct source of antimatter from space: cosmic rays. These high-energy particles, mostly protons and atomic nuclei, travel through space at nearly the speed of light. Scientists have sent sophisticated particle detectors into space, on balloons and satellites, to study these cosmic rays. The results confirm that it is being produced out there in space, but the amount they find is very small and perfectly consistent with what we would expect from secondary production. To solve the mystery of the missing antimatter, we need more than just a vague idea. We need a concrete physical mechanism. In 1967, the brilliant Soviet physicist Andrei Sakharov laid down the essential groundwork for any viable explanation. He was using the fundamental principles of physics to outline a set of 3 specific conditions that must be met for a universe to begin with a symmetrical state of matter and antimatter and evolve into the matter-dominated cosmos we see today. The first condition is perhaps the most obvious. The process must violate something called baryon number conservation. In simple terms, baryon number is just a count of particles like protons and neutrons minus the count of their antiparticles. Our current theories say this number must always stay the same. You can't create or destroy baryons on their own, only in particle-antiparticle pairs. To end up with more baryons than antibaryons, there must have been some process in the early universe that broke this rule. Sakharov's second condition is that the laws of physics must not treat matter and antimatter identically. There must be a violation of both charge conjugation or C-symmetry and the combination of charge conjugation and parity, known together as CP symmetry. If CP symmetry were perfect, any reaction that creates a baryon would happen at the exact same rate as the reaction that creates an antibaryon. To get a surplus of matter, there must be a subtle bias in the laws of nature favoring matter over antimatter. The third and final condition is that these processes must have occurred out of thermal equilibrium. In the very early universe, everything was a hot chaotic soup in a state of thermal equilibrium, where all reactions were happening at the same rate forwards and backwards. To lock in the asymmetry, the universe had to be changing rapidly, expanding and cooling so fast that the reverse reactions didn't have time to catch up. This rapid expansion would freeze the matter surplus in place, allowing it to survive and build the universe we know. The second of Sakharov's conditions, CP violation, is one of the most promising avenues of research because we know it actually happens. This was first discovered in 1964 in experiments involving strange particles called kaons. Scientists observed that kaons and their antiparticles did not decay in a perfectly symmetrical way. This discovery was so important it earned its discoverers, James Cronin and Val Fitch, the Nobel Prize in Physics. However, there's a big problem. While the CP violation predicted by the Standard Model is real, it is far too weak to explain the massive imbalance we see in the cosmos. When physicists plug the measured amount of CP violation into their cosmological models, the resulting matter-antimatter asymmetry is tiny, many orders of magnitude smaller than the 1 in a billion surplus required to build our universe. This discrepancy tells us something profound. It strongly suggests that there must be other undiscovered sources of CP violation out there. The Standard Model, for all its success, must be an incomplete picture of reality. One of the most popular theoretical frameworks is called supersymmetry, or SUSY. This elegant theory proposes that every known particle has a heavier, undiscovered superpartner. Another avenue of exploration involves grand unified theories, or GUTs. These theories attempt to go a step further than the Standard Model by proposing that at extremely high energies, like those present in the Big Bang, 3 of the 4 fundamental forces merge into a single, unified superforce. In these theories, there would be new, extremely heavy particles, often called X and Y bosons, that could mediate this superforce. The decay of these super-heavy particles in the rapidly cooling early universe could have directly produced more quarks than antiquarks. In recent years, a particularly compelling and elegant theory called leptogenesis has gained significant traction among physicists. This theory shifts the focus away from the quarks and baryons and onto their lighter cousins, the leptons, particularly the mysterious particles known as neutrinos. We now know that neutrinos are not massless, as was once thought, and they have the curious ability to change or oscillate from one type or flavor to another as they travel. The theory of leptogenesis proposes the existence of a new type of particle, a very heavy right-handed neutrino, sometimes called a sterile neutrino. These would have existed only in the extreme heat of the very early universe. According to the theory, as these heavy neutrinos decayed, they did so asymmetrically, violating CP symmetry and producing slightly more leptons than antileptons. This would have created an initial imbalance in the lepton sector of the universe. So how does an excess of leptons lead to an excess of baryons, the matter we are made of? The Standard Model contains a subtle known process, called a Sphaleron process, that was very active in the high temperatures of the early universe. This process can convert leptons into baryons and vice versa, effectively linking their fates. So the initial asymmetry created in the lepton population by the decaying heavy neutrinos would have been transferred over to the baryons. What makes leptogenesis so compelling is that it connects the mystery of matter's existence to the observed properties of neutrinos. Experiments around the world, like the T2K experiment in Japan and the Dune experiment in the United States, are currently measuring the properties of neutrinos with unprecedented precision. They are specifically looking for signs of CP violation in their oscillations. If they find it, it would be powerful, albeit indirect evidence in favor of the leptogenesis scenario. The quest to understand why we exist is not the work of a single mind, but a monumental effort spanning generations of brilliant scientists. One of the foundational figures was, of course, Andrei Sakharov, the Soviet physicist who, in 1967, first laid out the three crucial conditions needed to create matter's dominance. On the experimental front, the discovery of CP violation by James Cronin and Val Fitch in 1964 was a watershed moment. Their painstaking experiment at Brookhaven National Laboratory revealed that the laws of nature were not perfectly symmetrical after all. In more recent times, the field has been driven by large international collaborations. The work of the Babar experiment at Stanford and the Bell experiment in Japan was instrumental in confirming and precisely measuring CP violation in another particle system, the B mesons. Today, the torch is carried by thousands of researchers at facilities like the Large Hadron Collider at CERN. Scientists at experiments like LHCb are making the world's most precise measurements of CP violation, hoping to find deviations from the standard model that could point to new physics. They are the modern-day explorers, charting the unknown territories of the subatomic world. Their work is a testament to human curiosity and collaboration, continuing the legacy of figures like Sakharov, Cronin, and Fitch. They stand on the shoulders of these giants, using ever more powerful tools to probe deeper into the fundamental mystery of our own existence. Despite all our progress, the central mystery remains unsolved, and several key puzzles continue to challenge researchers. The biggest one is the sheer magnitude of the problem. Why is the known CP violation in the standard model so incredibly weak compared to what is needed? This huge discrepancy suggests our current theory is only a low-energy approximation of a much grander, more complete theory of nature. Finding new, more powerful sources of CP violation is the primary goal for an entire generation of physicists. Another major puzzle is the nature of neutrinos. These ghostly particles have already surprised us by having mass and the ability to oscillate. Theories like leptogenesis suggest neutrinos could be the key to the whole mystery, but to confirm this, we need to answer some big questions. Are neutrinos their own antiparticles? This is a fundamental question experiments are trying to answer through neutrinoless double beta decay. Finding this would be a revolutionary discovery, providing strong support for neutrinos playing the starring role in our cosmic origin story. Furthermore, we are still completely in the dark about the exact mechanism that violated the conservation of baryon number, Sakharov's first condition. While exotic theories provide potential mechanisms, we have zero direct experimental evidence for them. Ultimately, the most profound puzzle is how all these pieces fit together. Was the asymmetry created through quarks, or first in the lepton sector by neutrinos, or something else entirely linked to cosmic inflation or even dark matter? So we find ourselves at the end of our cosmic journey, yet standing at the precipice of an immense mystery. We've traveled back to the very first moments of creation, to a universe born in a flash of unimaginable energy. Our best theories tell us this beginning should have been perfectly symmetrical, creating one particle of matter for every single particle of antimatter. This perfect balance, however, held the seed of its own destruction. As the universe expanded and cooled, this matter and antimatter should have met and annihilated, cancelling each other out completely. The predicted result was a vast empty cosmos filled with nothing but a faint glow of light. And yet, we are here. The very fact of our existence is the most profound evidence that this perfect symmetry was broken. We live in a universe that is, as far as we can tell, made exclusively of matter. From the smallest microbe to the grandest supercluster of galaxies, everything is built from the same fundamental building blocks. The antimatter is missing. It wasn't a landslide victory for matter. It was a win by the narrowest of margins. For every billion particle-antiparticle pairs that annihilated each other in the primordial furnace, just one single solitary particle of matter was left behind. Our entire universe, with all its staggering complexity and beauty, is constructed from these leftovers, this 1 in a billion cosmic surplus. We are, in the most literal sense, the improbable survivors of a cosmic war of annihilation, that wiped out almost everything. Our existence hangs by a thread, a consequence of a tiny, almost imperceptible flaw in the fabric of creation. This brings us back to the central question: what caused that flaw? What mechanism tipped the scales? This shortfall points us towards the frontiers of knowledge, towards new physics beyond our current understanding. Whether the answer lies in the ghostly world of neutrinos, the elegant framework of supersymmetry, or a theory we haven't even dreamt of yet, finding it remains one of the greatest challenges in all of science. The quest continues on multiple fronts. At the high-energy frontier, giant particle accelerators are smashing particles together, trying to recreate the conditions of the early universe. At the precision frontier, experiments are studying the subtle properties of neutrinos. And at the cosmic frontier, telescopes continue to scan the skies for any faint, lingering signatures. So, the next time you look up at the night sky, remember the sheer improbability of it all. Remember that every star, every planet, and every atom in your own body is a survivor, a leftover from a cosmic battle that should have left nothing behind. We live in a universe that, by all rights, should not exist. The mystery of why it does is what drives us forward, pushing us to explore, to question, and to marvel at the grand, asymmetrical, and beautiful cosmos we are so fortunate to call home. The story is far from over, and the most exciting discoveries are surely yet to come. Thanks for watching.